Okay, so for the next set of slides, I'm going to talk about attention in more detail. So we've discussed already attention in the context of machine translation, but attention has led to a new class of neural networks that are known as transformer networks. Okay, and this material that I'm going to present today is actually quite recent. So it's not described in any of the textbooks that are associated with this course. So for this, there is a paper that was published in 2017 called Attention is All You Need. Okay, so it's a very interesting title, and it actually does suggest that perhaps we don't need recurrent neural networks anymore. And then a lot of the building blocks that people would design, let's say LSTM units, GRUs, and other things like this, essentially suggesting that we don't need them. All we need is really just attention. Okay, so let's see how this works. Okay, so it turns out that the concept of attention was first studied in the context of computer vision. And here, let's say that we have some images. We're going to recognize some objects. So as humans, let's say that we have a large image, and then we're looking for a tiny object. Then what we will do naturally with our eyes is roughly scan the image and eventually focus on some regions of interest and then eventually identify the object. And then when we identify an object, we eventually, I guess, focus precisely on the location where the object is. And then some studies have shown that our eyes are indeed focusing on the right regions when we do this type of identification. So I guess here an interesting question is there a mechanism in computer vision that could be similar, and would that be beneficial? And the answer is yes. So here, let's say that we have an image. Okay, this image doesn't appear very well on the screen. On my laptop, it looks better. So essentially, you're supposed to see some scene where there's a house and a tower here. So it's essentially two buildings, and then there's the rest of the scene around it. And let's say that we're doing object detection where we want to recognize buildings. So what this shows here is a heat map that's overlaid on top of the image. So that's why you don't actually see well the scene. But in any case, this heat map shows that the pixels or the region where buildings are more likely to be are right here in the red part. And if you look at it more carefully, it turns out that there is indeed a house here, and then there's a tower here. Okay, so now if you train some network to do some classification, an interesting question is when the network outputs a class, how can we trust that it comes up with the right class? And we could ask it, if you tell me that indeed there's a building in this image, can you show me where that building is, right? And this could be a nice way of at least validating, understanding what it thinks is a building in the image and whether it's correct or not. So here we can use attention to essentially see which pixels are aligned with the concept of a building, and then so the heat map corresponds to the weights here for the attention mechanism. So in this case, you could imagine having an attention mechanism over the entire image. So you've got weights with respect to all of the pixels, right? And then you try to see, I guess, which pixels would have some semantic meaning or some embedding that would be essentially aligned with the notion of the object that we're trying to recognize. And then so some researchers demonstrated that you can do this. And in fact here, attention can be used to highlight the important parts of an image that contribute to the desired output. So it's very nice in terms of explaining what is the decision process going on. And it can also be used to, as a building block as part of the recognition process. Okay, so this was in computer vision. Then in natural language processing in 2015, we saw the work about machine translation, where you can get your decoder to essentially peek or look back at what was the input sentence so that it doesn't lose track of what it's translating, and it doesn't have to remember completely the sentence. So this was an important breakthrough that allowed us to deal with sentences of arbitrary length, in fact, very long length. But then, further than that, in 2017, some researchers showed that we can use attention to develop general language modeling techniques. So here, language modeling simply refers to the idea of developing a model that would simply predict the next word in a sequence. So it could generate words. And then also, if, let's say, we've got a word missing somewhere in a sequence, then it could also recover that missing word. So language model is essentially just a model that can predict or recover words in a sequence. A lot of tasks can be formulated as language modeling problems. So whenever we do translation, you could imagine that it's just a sequence where we have a first part in one language, a second part in another language, and what we're really doing is just continuing the sequence where we're predicting words of the second part that happen to be in the next language. And if we're doing sentiment analysis, we can think of it this way too. So most of the tasks in natural language processing can be cast as some form of language modeling. And then what they showed is that we can also design some architecture that uses pretty much exclusively some attention blocks, and then they call that architecture a transformer. Okay, so we'll see in more details now those transformer networks, and they've become now the state-of-the-art for natural language processing, so they surpass now recurrent neural networks. Okay, so if we do a comparison between a recurrent neural network and a transformer network, turns out that the recurrent neural network has several challenges. The first problem that we've discussed a lot is how can we deal with long-range dependencies? And here the solution was, in fact, to combine the recurrent neural network with some attention mechanism. It also suffers from gradient vanishing, gradient explosion. The number of steps for training recurrent neural networks can be quite large, and this has to do with the fact that a recurrent neural network, we can think of it as essentially an unrolled network that is very deep, because when we unroll it, we have to unroll it for as many steps as needed for a corresponding sequence. So recurrent neural networks are effectively arbitrarily deep networks. And then, so they have lots of parameters. Those parameters are essentially correlated between each other because we in fact tie the weights from one step to another. And then, so the optimization tends to be quite difficult as a result, and it tends to require a lot of steps. Okay, so training a recurrent neural network usually takes a lot longer than a convolutional neural net or a regular feed-forward neural net. Beyond the number of steps, there's also the question of parallelizing computation. So today, GPUs have become key for working with large neural networks. And then what they really do is that they enable us to do some computation in parallel. But then if you have a recurrent neural network, what happens is that the sequence of steps, right, the computation has to be done sequentially. We can't process all those steps in parallel because of the recurrence. Okay, so there's an inherent problem here. We can't quite leverage GPUs as well in the context of recurrent neural networks. Now, if we consider transformer networks, we're going to see in a moment that because they essentially use pretty much exclusively some attention blocks, then there won't be any recurrence. And attention will also help us to draw some connections between any part of the sequence, so long-range dependencies won't be a problem. So in fact, long-range dependencies will have like the same likelihood of being taken into account as short-range dependencies. So that's not an issue anymore. Now, gradient vanishing and explosion will also not be an issue, because instead of having computation that goes linearly with the length of the sequence into a deep network for a recurrent neural network, in a transformer, we're going to do the computation for the entire sequence simultaneously and then just build several layers for that, but there won't be so many layers in practice. So gradient vanishing and explosion won't be as much of an issue. In terms of steps, it will take as well much fewer steps to train. And then, because there's no recurrence in those networks, we're going to be able to do the computation in parallel for every step. So this is really nice. So I guess we've got lots of great advantages for those transformer networks. OK, so to introduce transformer networks, let's review briefly attention. So we're going to see again attention, but more generally. So we've seen it already in the context of machine translation, but now let's think about attention as essentially being some form of approximation of a select that you would do in a database. So in a database, if you want to retrieve some value based on some query, and then also based on some key, right? Then there's some operations that you can do where you can use a query to identify a key that aligns well, and then simply output the corresponding value. So we can think of attention as essentially mimicking this type of retrieval process, but in a more fuzzy or probabilistic way. OK, so let me draw a picture just to illustrate how things would normally work in a database. And then we'll see that in our case, we're going to enable the same type of computation that would normally happen in a database, but using this equation here. OK, so let's say I've got a query. And then I've got a database. So in my database, let's say that I've stored some keys with associated values. OK, so I've got my database. Now, when I issue a query, right, I will see how well this query aligns with different keys. Perhaps the key that is the right one is, let's say, key number 3. Then what I would do is essentially produce an output that corresponds to the value. OK, so retrieval in a database would more or less correspond to this. And now an attention mechanism is essentially a neural architecture that mimics this type of process. And the way we're going to mimic this is by using the following equation. So here we're going to measure what is the similarity between our query Q and each key value Ki. And then this similarity is going to return a weight. And then we'll simply produce an output that is a weighted combination of all the values in our database. Now, normally with a database, when we do retrieval, we simply return one value. And this would correspond here to finding a similarity between the query and some key. where the similarity would have value 1, and then all the other keys, the similarity would be value 0. So if we have this, if we've got a similarity function that essentially produces a one-hot encoding, right, then we would effectively just return one value. Now in practice, because we'll want to embed this as part of a neural network and be able to do backpropagation to differentiate through that type of operation, then it'll be useful for us to think of the similarity as instead computing a distribution. So I guess weights that are between 0 and 1. And then even if we have multiple keys that have some similarity, the idea is that we're going to produce a value that's going to be a weighted combination based on the weights. Okay, so I guess we can think of this as like a generalization of the mechanism for a database where we make the retrieval process become a convex combination or a weighted combination of the values for which the keys have a high similarity in the database. Okay, so let's draw now a neural architecture that will correspond to this attention mechanism. So it's going to be essentially the same as what we've seen already in the context of machine translation, but now we're just going to make it domain agnostic. So you're going to see more generally what attention really corresponds to. Okay, so let's say that I've got key 1, key 2. Actually, let me shift this a little bit. Key 1, key 2, key 3, and key 4. We're going to have our query. And let's have S1, S2, S3, and S4. Now, query is going to influence the computation of each one of those things. So here what I've drawn is a first layer where, starting with the keys, I'm going to compute a similarity measure. So these S's correspond to similarity. Okay, so here Si is going to be equal to some function of the query with respect to some function of the query Q and the key Ki. And now there's many functions that we could consider. So let me suggest a few. The first one could simply be a dot product. So just like this. Okay, so the similarity, if we think of the query and the key as just embedding vectors, right? If I want to measure their similarity, a simple thing is just to compute their dot product. So that's something common. A variant on this is going to be a scaled dot product. Okay, and then here D is the dimensionality of each key. Okay, something slightly more general. We could also have Q transpose WKI. So I'll call that a general dot product. And then finally, let's have W transpose Q of Q plus W transpose K, Ki. So this will be an additive similarity. Okay, so this first layer is computing the similarity between some query Q and each key in our database or in our memory. And to do this, there are many choices. Some common choices in practice are just to do a dot product or scale the dot product by dividing by the square root of the dimensionality. This has the benefit of simply keeping the dot products in a certain scale. Now, more generally, we can also project the query into a new space by using a weight matrix W, and then after that, taking a dot product with Ki. And then another one is just to take the sum of some combination of Q and Ki, and this is known as some form of additive similarity. Now, you could think of other types of similarity. For instance, earlier in the course, we talked about kernel methods that also measure similarity. They do this by essentially mapping two vectors into a new space through some nonlinear function. So we could have as well in here some form of kernel similarity too. Yeah?
Sorry. Can we use a convolutional method instead of the W in the third method? I mean, convolving a kernel with the QT and then doing the dot product.
Okay, so in this case, we're not going to have convolutions, but here are you suggesting that instead of comparing the query to every k, we could just do it with respect to a subset of the k's?
The W is a big matrix which just product with all the weights, but we can have a window which is.
Oh, so this W, think of it as more like we're simply transforming our query to be in the same space as the keys. So, okay, to give you a concrete example, let's say that we're doing question answering, and then we would like to, let's say we have a database of possible answers. We've got a query, and now let's say we've got an embedding of every answer that corresponds to a key. Now the query is a question, so we can embed it as well. And now the problem is that depending on the type of embedding we compute, if those embeddings are simply computing the semantic meaning of these sentences, right? There's no reason for us to expect that the question and the answer have the same meaning, right? So in fact, they should have different meaning because the answer is supposed to provide something that the question doesn't have, right? But still, then what you can do is map them into a new space where there we could interpret the question and the answer as really being things that we can compare directly, and then this matrix W serves that purpose. Okay, so it's just a high-level intuition, but the idea is that if you're not confident that you can compute the similarity directly, then you can allow your neural network to learn a mapping W. So here, W is a set of weights, and it's a matrix that will essentially map our query into a new space, and then it will just learn what that new space should be. Okay, so that's our first step. Now the second step, or the second layer after this, will be to compute the weights. So we'll have A1, A2, A3, and A4. Those weights, they depend on everything. Okay, so here, this would be done through a softmax. So essentially, AI is going to be equal to the exponential of Si divided by the sum over j of the exponential of Sj. Okay. So yeah, so here it's a fully connected network, but not in the classical sense. It's more, I'm just showing what hidden nodes are used in computing these weights. This is a softmax. We don't have any weights. All we're doing is just computing this expression. Okay, and then after this, we're going to have our weighted combination. So what I've shown here is that we multiply A1 by V1, right? So this means that we multiply them, then we add them to the product of A2 by V2, we add this to the product of A3 times V3, and so on, and then this produces the attention value. Okay, so the attention value is just the sum over I of AI VI. Okay? So I guess you see this is a general scheme where we have some query, we have some keys, and then we're going to produce an output where the output is really a linear combination of some values where the weights come from some notion of similarity between our query and the keys. Okay, any questions regarding this? Yeah.
For the general dot product, would we want the basis of that W matrix to span like the key space?
Right, so here the W matrix should span the space that we care about. Now, we don't specify W, right? These are variables that are going to get optimized by the neural network itself. So that's the beauty of this, right? So here, again, W in general indicates weights that are parameters or variables in the neural network. And then whatever the task, right, we're going to do backpropagation. And then these weights are going to get adjusted so the neural network is going to learn on its own what might be a good space to project Q into so that then we can take a dot product with K. Yeah?
AIs, are they like a vector or are they like
Oh, good question. Okay, yeah, the AIs are scalars. So I guess, okay, so the KIs are vectors. Okay, the SIs are scalars. The AIs are scalars. And then the VIs are vectors.
what do this are they're like scalars? Attention means like it's respect to all the words, right? It's respect output is with respect to all of the words.
Yeah, so here, these scalars are weights, and then there's going to be a weight like this for every possible word. Like if we're doing machine translation, and now we're about to produce an output, and we want to compute the attention with respect to the input words, then we're going to have essentially one one weight per output word, and then the VIs are essentially going to be the hidden vectors associated with each input word. Okay, so in fact, this is what I've got here on this slide. Right, so as a concrete example, we've talked about machine translation in a previous set of slides. And here, if I simply use as a query SI, the hidden vector for the ith output word, and then for the keys and the values in this particular setting, I'm going to have the same thing. So both the keys and the values are going to be the HJs. These are the hidden vectors for the input word. That allows me to essentially compare my, my hidden vector for an output word to each one of the hidden vectors for an input word, and then essentially combine them together to produce a context vector that reflects what are the words that I'm interested in decoding next or translating next. Yeah?
I was wondering how you handle the variable length documents. I mean, without any sort of recurrency, how you can remember about the previous word.
Okay, great question. Yeah, so we haven't talked about yet what is a transformer. All I'm doing so far is just explaining in a general form what is the attention mechanism, but I believe it's coming up in a few slides. All right, so we've discussed all kinds of networks, and more recently the focus has been on sequential data. We've seen hidden Markov models, then recurrent neural network, and now we're talking about transformers. So I want to go back and discuss in more detail the transformer network that was presented in 2017. So this network is special because, as we discussed, it gets rid of recurrence. So this was a major thing. So recurrences mean that the optimization tends to take longer for two reasons. The number of iterations, so the number of steps in gradient descent will be higher. And also recurrence means that we have several operations that are going to be sequential, and then we cannot parallelize them as easily. So the beauty of having a GPU is that in principle you can parallelize lots of operations, but if these operations are going to be sequential, then you cannot, right? So we would like to reduce as much as possible recurrence. Okay, so on this slide here, we've got a picture of the transformer network that was proposed in 2017. And this network has now displaced pretty much recurrent neural network for sequential data. So this was a major shift in the thinking that people have now with respect to sequential data. Okay, so if we take the example of machine translation, so this network, even though it's not obvious, has two parts. The first part that corresponds to an encoder, the second part that corresponds to a decoder. And here you see in machine translation, you would use the encoder to encode your initial sentence, and then you would use the decoder to produce a translated sentence. Now, this will process an entire sentence in parallel, as opposed to a recurrent neural network that will essentially process one word at a time in the sentence. So if you look carefully, you see the inputs here would actually be the entire sequence of words. So we would feed them all in at once, and then they would get embedded, and then after this we would add a positional encoding. I'll come back to this later on in a few slides, but this is important essentially to make sure that we can distinguish words that occur in different positions within a sentence. The problem is that if we don't have a positional encoding, then we would effectively have a model here that treats the word as if it was a bag of words as opposed to a sequence. And then we all know that in languages, the sequence actually matters, so the ordering matters. So we need to still capture this information, and then so the positional encoding achieves that. Okay, so Now the important part of a transformer network is essentially this block here. It consists of two subparts. So there's a multi-head attention and then here a feed-forward neural network. Now the multi-head attention is really where all the good stuff happens. So here the idea is that we feed in, again, a vector that would consist of subvectors of all the words that we have in our sentence. And then the multi-head attention is going to compute the attention between every position and every other position. So we have vectors that embed the words in each one of those positions. And now we simply carry out an attention computation that would essentially treat each word as a query and then find some keys that correspond to the other words in the sentence, and then take a convex combination of the corresponding values. So here the values are going to be the same as the keys, and then take a dot product of that to produce a better embedding. So the idea is that this multi-head attention will essentially take every word, combine it with some of the other words through the attention mechanism to essentially produce a better embedding that merges together information from pairs of words. Now when we do this in one block, we essentially look at pairs of words together. But now if we repeat this multiple times, so this n times here means that we're going to have this block that's going to be repeated n times. We're going to have n stacks of those blocks. And now you see in the first block we look at pairs, and the second block we're looking at pairs of pairs, and then the third block we're going to look at pairs of pairs of pairs. So essentially we're combining now more than just two words, but groups of words that get larger and larger and larger. Okay, so that's what the multi-head attention does. Then we have on top here another layer that's called add and norm. This is essentially adding a residual connection that takes the original input to what comes out of the multi-head attention, and then it normalizes this. So here norm is essentially a layer normalization. We'll come back to this in a second, but it essentially means that we take all of our entries and then we normalize them to have zero mean as well as variance 1. Then we feed this into a feed-forward network. There's again a residual connection and then a normalization. So this block is repeated n times so that then we can combine not just pairs of words, but pairs of words and so on. So that eventually you see you can combine together all the words in the sentence. Okay, so the output of this is going to be, again, a sequence of embeddings. There's going to be one embedding per position. Intuitively, the embedding at that position captures the original word at that position, but also information from the other words that it attended to throughout the network. Okay, so you can think of this as essentially just a large embedding of all those words corresponding to each position. So that's our encoding of the input sentence. Then after this, we have the decoder, which will do something similar, but obviously the main purpose of the decoder is to produce some output, not just to embed, but produce some output. So that's why we're going to have some additional stuff on top here, where we have a softmax that produces some probabilities for, let's say, outputting a label in each position. Okay, now inside the block, so this block will also repeat n times. What we do is we have first a multi-head attention that looks at simply combining output words with previous output words. And then there's another block of multi-head attention that now combines output words with input words. And then finally, a feed-forward network again. Okay, so here you see we have two layers of attention. The first layer is really just self-attention between the output words. So now the problem though with output words is that when you generate a sequence as output, you can only generate the next word based on the previous words. So when you do the attention, you need to be careful to make sure that you only attend to previous words. And that's why this one is called a masked multi-head attention, because we can mask the future words so that each word is only attending to the previous words. The second multi-head attention here is now combining, making sure that each position in the output is attending to positions in the input. So this is where, a bit like in machine translation, whenever you want to produce an output, it's good if you can kind of peek and look back at what was your input sentence. And here we're going to look at the embeddings of each position in the input. So that's why you see we've got these arrows that go in. Okay, and this will be repeated n times again, so that the idea is that we gradually build up combinations and then get better and better embeddings until we produce an output. And here the output can be a distribution over the words in the dictionary. Right? So for every position, there's a word that we're trying to generate, and then we're going to compute some distribution over the words in the dictionary. Any questions regarding this slide? Okay, good. All right, so in the transformer network, perhaps the most important part is this multi-head attention. So I'm going to draw on the board what this corresponds to. Now, mathematically, the multi-head attention is essentially this expression that decomposes according to these operations. Okay, so for the multi-head attention, as we talked about last class, whenever we want to design an attention mechanism, the general way of thinking about it is that we have some key value pairs, just like in a database, and then there's a query that we're going to compare to each keys, and then the keys that have the greatest similarity are going to have the highest weights. And now we can take a weighted combination of the corresponding values to produce the output. So we're going to feed V, K, and Q into some linear layer. Then after this, we're going to compute a scale dot product attention. Then we're going to concatenate these outputs. Then we'll have another linear layer. And then the output of this is going to be our multi-head attention. Okay, now this is called multi-head because in reality, and I haven't drawn this yet on the board, we're going to compute multiple attentions. So here, when we take a linear combination, perhaps there's different, we can think of this linear combination as really being a projection of the values V, same thing for K, same thing for Q, and we could consider several projections. So here, I'm going to use this to indicate that I could compute 3 different types of projections by looking at 3 different linear combinations of the values. Same thing for K. Same thing for Q. So that I get essentially 3 different projections. Now, each one of them, I can now compute a scale dot product attention. So I will get 3 scale dot product attention. And the way to think about these different linear combinations, these different scale product attention, is that it's a bit like feature maps in convolutional neural networks. So we saw that in convolutional neural network, you can compute multiple feature maps simply by having different filters. So here, these linear combinations are a bit like different filters, although in this case, you can think of them as more like projecting or simply changing the space in which the values reside. Okay, so here this will give us different projection or different spaces, a bit like multiple filters into a convolutional neural net. And then when we compute the scale dot product attention, then for each projection there's going to be a different scale dot product attention. So we're going to get multiple of them, and that corresponds more or less to having multiple feature maps. That's the same intuition. So then this concat layer is going to concatenate these different scale dot product attention, and then finally we take a linear combination of them, and this gives us a multi-head attention because we essentially computed multiple attentions. So here there's 3 of them. So we can think of these as H. So this would be the number of heads in multi-head attention. Okay, so the idea is that there's 1 head per linear combination. So here there's 3 of them. In general, there's going to be H of them, and that's where the idea of the name multi-head comes from. Okay, any questions regarding this? Good? Okay. All right, so beside just a regular multi-head attention, we also have in the decoder a mask multi-head attention. And here, the idea behind a mask multi-head attention is that some of the values should be masked, meaning that the probabilities should be nullified so that we don't create any combinations. So for instance, in the decoder, when we produce the outputs, let's say we're doing machine translation, so we have a sentence, let's say in English, then we're translating that into French. We start producing the words in French. When we produce a word, right, then it's okay for that word to depend on the previous words in the translation because we're generating them sequentially. But it doesn't make sense for that word to depend on the future words because we haven't produced them yet. Right? So here what we need to do is to essentially change our attention mechanism so that we would nullify or effectively remove links that would create dependencies on words that we haven't generated yet. And so this is what we call a mask multi-head attention. Okay, so here the main difference is that in the attention mechanism, normally we just compute a softmax according to this expression. But now instead, with a mask attention, we're going to add a mask here that will effectively produce some probabilities that are 0 for the terms that we don't want to attend to because they would be future terms. So here you see in a softmax, what I normally do is take the exponential divided by the sum of exponential. So now if I add a mask, which is a matrix of zeros and minus infinity, so adding minus infinity, when I take the exponential of minus infinity, it gives me 0. So this has the effect of ensuring that the probabilities of certain items here are going to be 0, because I'll take the exponential of minus infinity, and this will have the same effect as removing connections. So at some level, you can think of this as a form of dropout, but here it's not a dropout in the same sense that we saw it at the beginning of the course, right? So dropout for regularization, you would drop out some connections or remove some connections at random according to some distribution. Here, we remove connections that are essentially pointing at words that we haven't produced yet. So this is more like a deterministic type of dropout, if you wish, because we would never have those connections. So here, as opposed to sampling those connections with a distribution, you see we use a mask, and then inside the softmax, the mask will have the effect of nullifying some of the connections because the exponential of minus infinity will be 0. Any questions regarding this? Yeah?
Sir, for masking, why they used adding with a matrix with minus infinity? Why not just doing some sort of Hadamard production, pairwise production?
Yeah, okay, good question. So yeah, here, in the paper, they add a mask with values that are minus infinity. Now, perhaps the more intuitive approach would simply be to multiply the softmax by some sort of Hadamard product with values that are 0 and 1. Now, when we do it outside with values that are 0 and 1, what happens is that the softmax produces a distribution that adds up to 1. Now we're going to nullify some of those probabilities, and then the sum of the probabilities that are left is not going to add up to 1. Whereas if we do it inside, right, by adding a matrix that might have values that are minus infinity, it means that when we take the softmax, these are going to have 0 probability, but then all the other values are going to have probabilities that still sum up to 1. So this ensures that we still have a proper distribution. Okay, and if we just go back to this slide, you see what happens is that when we produce an output, let's say I produce my first word here, then that first word could be fed as input for the next position. Right? So when I want to produce a word for a certain position, it's okay to look at the previous words. And this is where the mask multi-head attention will apply. So we're going to have a mask. It's a matrix that would essentially be lower triangular that has essentially values that are 0 in the lower triangular part and minus infinity in the upper triangular part to essentially nullify everything that happens in the future. And the other thing that might not be obvious is that it looks like here when we've got some output, it gets fed back in as input here, and that looks like it's creating a recurrence. So here, this is not creating a recurrence per se, simply because there is a method for training known as teacher forcing, where the idea is that when you train the network, you have both what is the input sentence and the output sentence, and then you can simply say, well, let me assume that my outputs are correct everywhere, so I'm going to feed that as input here. So I'm going to feed in what are the correct output words for the previous positions, and then I'll simply try to predict what is the next word based on that. Okay? So with this scheme that is known as teacher forcing, then you can essentially decouple the output here from the input here, and we don't have any recurrence relation in training. Now, at test time, then what happens is that you really have to execute this network with the recurrence relation, but that's okay. So where there's really a gain is at training time. So training is what takes a long time. And if we can remove all recurrence relations so that we can do all the computation in parallel, this will be a lot faster. And then through this teacher forcing trick, then what we do is we simply assume that we have the correct output words for the previous words, and then we feed them in here as if they were given to us, and then we simply try to predict what is the next output. Any questions regarding this? Okay, let's continue. Okay, so the other important layers are the normalization layer and also the positional embedding. So the normalization layer is actually quite important and quite interesting. So it's this layer that we saw right here. So on top of every multi-head attention and feed-forward network, there's here a normalization layer. So what this does is that it helps to essentially reduce the number of steps needed by gradient descent to optimize the network. Here, whenever we've got a network with multiple layers, we've got weights in each layer, and then those weights are going to be trained by gradient descent. But when you look at the formula for the gradient, it's often the case that to compute the gradient of one set of weights, then it depends on the output of the layers below and also what is being computed in the layers above, right? So it depends on what is being computed below and above. Now, the problem is that if we're still adjusting the weights below and above, now when we compute the gradient, then things are not going to be stable. So at some level, it's like we'd rather wait till all these other layers have stabilized, and then we can optimize the gradient in the middle properly. The problem is we can't do this because we have to optimize essentially all of those layers simultaneously. And then there's this effect where you see you change some weights that affects the other layers, then you change those weights that affects the layer that you just changed, and so on. And then so it makes the convergence quite slow because we've got all these interdependencies. Now there's no way of completely getting rid of the interdependencies because if we did, that would mean that we're essentially breaking our network into parts that are not connected anymore. But one thing we can do is to do some normalization. When we normalize, what this does is that it ensures that the output of that layer, regardless of how we set the weights, are going to be normalized. They're going to have a mean of 0 and a variance of 1. So the scale of these outputs is going to be the same. Okay, so now to obtain the same scale, what we can do is, you see, for each hidden unit, we can subtract from it the mean. So the mean would be just the average, the empirical average like this. And then we can divide by the standard deviation, which is here the square root of the empirical variance. And then there's also a variable g, which is known as the gain, that's added to essentially compensate for the fact that we've just normalized. But the idea is that with this approach, then we can ensure that, you see, if g is set to 1, then this would ensure that h is always normalized with 0 mean and variance 1. And therefore, you see, if there's some gradient computation that depends on the output of that layer, the outputs of that layer are always going to be at the same scale. They're going to vary, but at least they're going to remain on the same scale. And then, as a result, the outer gradients, when we compute them, they don't have to adjust simply because we're changing the scale of those outputs. So that reduces the dependencies between the layers, and it tends to make the convergence faster. Okay, any questions regarding normalization? Okay. Perhaps one thing I should say as well, some of you might have heard about batch normalization. So this is closely related to batch normalization. But the main difference is that we're doing the normalization at the level of a layer, whereas batch normalization would do it for one hidden unit, but by normalizing across a batch of inputs. The advantage of layer normalization is that we don't need to worry about how large our batch is. So batch normalization only works well if you have fairly large batches. And this here we can feed in one data point at a time. We can have mini batches that are very small. In fact, we can be in an online or streaming setting where we just feed in one data point at a time, and we can still do the normalization, and it still has the same effect as batch normalization in terms of decoupling how the gradients evolve in different layers. Okay, so, the other part that is important is the positional embedding here. So if I just go back, we introduce a positional embedding right after the input embedding. The idea is that with the attention mechanism, it doesn't care what's the position of the words. So the words could be all shuffled. We could consider them as a bag of words. And if it wasn't for the positional embedding, right, we would get the same answer. And at some level, that's not good because sentences, the ordering of the words is important in order to tell us what's the meaning, right? So the ordering does carry some meaning. So we need to still capture some of that information. And here, this is really an engineering hack, okay? So it's not clear that this is really the best way to still capture the ordering, but the idea is that we're going to, you see, we have already an embedding here that is supposed to capture information about each word. Now let's just make that embedding capture information about the word and also its position. So we're simply going to add a vector that is known as a positional encoding, and that vector is going to be different depending on what is the position. So it's just a vector that embeds the position, which is an integer, and then we add that to the embedding of the word. Okay, so what's the precise formula for the positional embedding? It's given here. The idea is that we have a position, which is an integer, and then we embed it into a vector. So it's a vector with multiple entries, and now each entry is going to be computed according to the sign of the position divided by 10,000 to the 2i divided by d, or the cosine of the position divided by 10,000 to the 2i divided by d. Okay, so here, just to illustrate, let me draw something on a board. Yeah, so we have the position. We're going to compute, based on this, a position embedding. So here, this is a scalar, and this is a vector. Okay, so the idea is that we already have an embedding for the word, and this embedding is a vector. Now we want to encode as well the position. So obviously there's multiple ways in which we could do this. The simplest could just be to have an integer for the position and maybe append that or concatenate that with the embedding of the word. But in this work, the authors simply chose to add to this a vector, and then it's going to be a vector of the same dimensionality as the embedding of the word. So often these vectors are going to be hundreds long. And now how do we go from a scalar to a vector? Well, this is where the formula gives us a way to obtain a different value for each entry of the vector. So you see, for the even entries, we're going to compute the sign of this, and then for the odd entries, we're going to compute the cosine of this. And here, really, this is something that's debatable, okay? We could consider perhaps different ways of coming up with a positional embedding, but at least the key is that it carries information about the position, which allows us to distinguish each word so that then our sentence still retains ordering information. Yeah?
So we only add them together, I mean the word embedding and positioning embedding, doesn't it damage the word embedding?
Yeah, very good point. So yeah, just adding the positional embedding to the word embedding could maybe affect the information that is included in the word embedding. And yeah, my gut feeling as well is that it might just be better to concatenate this so that we don't lose the information. But in any case, that's what the authors chose to do, and it seems to work relatively fine. Okay. All right, so if we compare now a transformer network with a recurrent network or convolutional neural network, we get the following complexity estimates. So here, the transformer network is the one called self-attention. In a self-attention network, what happens is that in each layer, here I guess a layer would consist of n positions. So let's say we've got a sentence of size n, so we're going to have n positions. And now when we compute an embedding for each position, it would have dimensionality d. So the order of computation, the complexity of the computation in one layer is going to be order n square, simply because for every position, we're going to try to attend to every other position, so all the pairs is n square. And then for each pair, we're going to compute an embedding of dimensionality d. So that's the complexity we get. Now, the benefit is that if we want to capture long-range dependencies, then the maximal path between any two positions is just one, simply because we have our attention mechanism that combines in one operation essentially every pair of words. So now information can flow between pairs of words in one step. So then we don't have to worry about information being lost, like in a recurrent neural network, where the first word that we process gets embedded, but then after that, when we process additional words, then this embedding changes, and eventually it loses information from the first word. Right? So here it allows us to essentially combine together information about pairs of words immediately, so that's a good thing. So here a path length of size 1 is great. And the other important aspect is that here there's no sequential operation, in the sense that we have a sentence of size n, but now we essentially process all of the words simultaneously. We're going to look at every pair of words simultaneously. So I guess this is where we have this n squared that creeps in. But on the other hand, all of this can be parallelized. So today with GPUs, we want to exploit parallelization, and it's better to, in fact, not have to process the words sequentially, but then to do everything in parallel. So even though we have a factor n square, this n square in practice might not be so bad, simply because we're going to do a lot of those operations in parallel. In contrast, a recurrent neural network will have this complexity. So so I guess here the idea of a recurrent neural net having multiple layers, the way to think about it is that normally we think of a layer as being every word that we process, but then another way of thinking about it is that you could have stacks of recurrent neural networks. So we haven't talked about this, but it's actually something common that people would do in practice, and that makes the network even more complex and heavier to train. But if you have stacks of recurrent neural networks, then here we would have some computation. Let's say that we have n of those stacked together, so the computation would be n times d squared in just one layer, in one stack. Okay? And then the d squared comes from the fact that we have an embedding of size D, and now if you consider a GRU, an LSTM, or even just a linear unit that produces the next embedding of size D, then typically you're going to have a matrix of weights that's D by D that will essentially multiply this hidden vector in order to get the next hidden vector. So that's how the D square shows up. We have sequential operations because we have to go through the entire sequence, and then the path length is it can be up to size n, because if you want to combine information from the first and the last word, then you've got a long path to go. Okay, so in general, this will be quite advantageous. It will help to reduce computation and improve scale, improve scalability quite a bit. Any questions regarding this? Okay. Now, in the paper in 2017 regarding transformers, there was a comparison done for machine translation. Here they compared English to German. They did translation between English and German as well as English and French, and then they compared a bunch of models, and their models are down here. Okay, so they've got a base model and then a bigger transformer. If you look at the results, they're not really outstanding. I mean, they're improving, at least in this case for English-German, improving a little bit the accuracy. So here blur, if you recall, is a measure of precision where you look at the percentage of words in the output translation that are part of some human translation, roughly speaking. So the higher, the better is the score. And then so I guess they outperform a little bit. Here they came close to the state of the art. But now what's beautiful is the fact that they reduce the computation significantly. So here, I mean, those numbers look horrible because when you see 10 to the 18, I mean, that's scary. And then 10 to the 19 obviously is worse, 10 to the 20, 10 to the 21. But now the difference between 10 to the 18 and 10 to the 19, that's a factor of 10. Right? So something that would take 10 days now might take 1 day. And with respect to 10 to the 20, that's a reduction of a factor of 100. And for 10 to the 21, that's a reduction by a factor of 1,000. So this is a major reduction in terms of the training time. And here, I'm not sure, I don't recall from the paper whether that takes into account parallelism or not. But in any case, this gives you a sense about the fact that really a big advantage is that it reduces computation while still achieving the state of the art. Okay. Any questions regarding this? Good? Yeah?
Does training cost depend on the language for the other models, but not for the transformer model?
Okay, so that's a good question. Yeah, so the training cost is different for different languages. It might have to do with how much data they use for training, but then presumably that would have an effect here too. I'm not sure. Because yeah, presumably there should be a difference here too. I'm not sure. We'll have to look it up in the paper. Okay, so transformer was essentially the starting point of a new class of neural network that do not rely on recurrence. And then another important type of transformer is known as GPT, and then I guess an improved version known as GPT-2. So these were proposed in 2018. Here, when they were proposed, the idea is that they did unsupervised language modeling. And here language modeling is a general task where you say, I've got a sequence of tokens, a sequence of words, and I'm simply going to predict what the next word is. And it turns out that a lot of tasks in natural language processing can be formulated as some form of language modeling. So if you take machine translation and you concatenate the input sentence and the output sentence into just one long sequence, and now let's say you've got a language model that essentially simply predicts what is the next word in the sequence, and furthermore, let's say that this language model doesn't care about whether it's English or French or any language, it just predicts the next word in the sequence, then you can train it to essentially do translation, right? So you just feed it with the inputs, and then it will predict what the next words are in the other language. So a lot of tasks can be formulated this way, where you just create a sequence, and then just by the virtue that it's going to predict the next thing, if the next thing is what you care about, maybe it's a classification, maybe it's another sequence of words, then you can do all of those tasks with a language model. So here they did something really interesting, where they trained some decoder transformer. So because they were only going to predict the next word given the previous word, and then there was no need to really separate some input sequence from an output sequence, then they did not really need to have the encoder part. So in the transformer architecture, they actually got rid of the encoder, and then they worked only with the decoder. So the decoder attends to the previous outputs, which could be considered the inputs, and then it never attends to the future output, so it can just generate sequentially, right? So that's the main thing. Compared to the transformer network, they essentially just got rid of the encoder. The other thing they did here is what they call zero-shot learning. So it means that they simply took a very large corpus, they trained on this corpus to predict the next word in the sequence, irrespective of what the task is. And then they simply applied this to different tasks where the network was not tailored or was not fine-tuned for that task. It was just trained, generally speaking, to predict what the next word is in the sequence. And then so they did this for some tasks that correspond to reading comprehension, translation, summarization, question answering. And we can see in blue their performance. Here the performance improves as we increase the number of parameters for the language model. And then they compare to state-of-the-art techniques. Now, their approach was general. It was not trained specifically for a particular task, whereas in this case, for instance, PGNet, DRQA, DRQA plus PGNet, and so on, are trained specifically for that task. So what's beautiful is that in a completely unsupervised fashion, without really being tailored to that task, they managed to come close to the state of the art, and then it's fairly general. It can be used for many tasks, right? So you can see the results. It doesn't beat the state of the art on most of those tasks, but it does beat at least some techniques that were tailored. And then I guess if you keep on improving, it suggests that those curves would lead to further improvements. Okay, any questions regarding GPT? Okay, so let's continue. Now GPT was not the last one. There's another one called BERT that has become quite popular, and it was proposed this year. BERT stands for bidirectional encoder representations from transformers. So it's another variant of the transformer network, and the main advance that is being proposed here is that instead of just predicting the next word in the sequence, why don't we predict a word based on the previous word and then the future words? So there's lots of tasks, including machine translation, where if you think about it, if you're given a sentence as input, there's no reason why you have to really produce the sentence as output sequentially, one word at a time. You could work on your translation by coming up with some sections of the translation and gradually building up your translation, but you don't have to do it perfectly sequentially. right? So a lot of tasks are actually like that. And then what it means is that you could take advantage of what comes before and what comes after. So it's a bit like bidirectional recurrent neural networks that improve with respect to unidirectional recurrent neural networks. So here it's a bidirectional transformer, and naturally it does better than GPT. So they tried it on a bunch of tasks, in fact 11 tasks, and then here what they did is they did unsupervised pre-training, just like GPT, but then to really compete with the state of the art, they did some further fine-tuning with data specifically for that task. So yeah, their proposal is we first train a general network unsupervised with lots of data, and then we fine-tune the parameters by doing some further training with data specifically for that task. And when they did that, then they obtained those results. And here this is quite impressive because, okay, they improved the state of the art on 11 tasks. And if you look at some of those tasks, like for instance this task here, they improved the state of the art from 45 to 60. Okay, so this is a major improvement. Okay, any questions regarding BERT? All right, so BERT is, again, not the last network. There is another network that was just made public about a month ago called XLNet. And now XLNet beats BERT as well. Okay, I don't have a slide for it, but I can tell you, roughly speaking, that the main difference is that BERT essentially assumes that we've got, everything in the window before and after, whereas XLNet allows missing inputs in a sense, and then tends to generalize better by looking at different subsets of words before and after. And as a result, yeah, it tends to generalize better, and then it improves again on a lot of tasks. I don't remember what the number of tasks is, but in general, it beats BERT across the board for most tasks. Okay, so this has been a fruitful direction, and then it's become quite clear now that those transformer networks can perform quite well, both in terms of accuracy and also in terms of speed. And now it becomes questionable what the future of recurrent neural networks will be. Okay, any questions regarding this? All right. Okay, so this concludes this set of slides.